We want to solve the separable differential equation for u of t. We're given du dt equals e raised to the power of 6u plus 9t. We also want to find the particular solution given u of 0 equals 3. Normally when solving a separable differential equation, we want to write the differential equation in the form of a function of y times dy equals a function of x times dx. But because we're looking for u of t, we want to write our differential equation in the form of a function of u times du equals a function of t times dt. So to begin, let's write the given differential equation in differential form. If du dt equals e raised to the power of 6u plus 9t, then differential u is equal to e raised to the power of 6u plus 9t times dt. Now here, because we're adding the exponents, we can write this as a product where the basis would be e. So we can write this as differential u equals e raised to the power of 6u times e raised to the power of 9t dt. Notice how this exponential contains the variable u, so we want this factor to be on the left side of the equation with du. To do this, we can multiply both sides of the equation by e raised to the power of negative 6u. When we multiply e to the 6u and e to the negative 6u, we add the exponents, giving us e to the 0, which is equal to 1. So this product is equal to 1, and therefore we have e raised to the power of negative 6u du equals e to the 9t dt. Now because we have a function of u times du equals a function of t times dt, we can now integrate both sides of the equation and solve for u. Notice in both cases, we have to perform substitution to integrate. We're already using u, so let's use v. Let's let v equal negative 6u. Notice differential v would be negative 6 du. So if we divide both sides by negative 6, notice how du is equal to negative 1/6 dv. So when we integrate this, we'll have an extra factor of negative 1/6. So on the left side, the antiderivative of e to the negative 6u with respect to u would be negative 1/6 e to the negative 6u plus c, but we'll also have a plus c on the right, so we'll only put plus c on the right. Equals, now here we'll have a similar situation where if w is equal to 9t, dw is equal to 9 dt, dividing both sides by 9, notice how dt is equal to 1/9 dw. So the antiderivative of e to the 9t with respect to t would be 1/9 e to the 9t plus our constant c. Now we need to solve this equation for u. Let's begin by multiplying both sides of the equation by negative 6. Let's go ahead and call this c sub 1 instead of c. So now we'd have e to the power of negative 6u equals, this would be negative 6/9 e to the 9t, or negative 2/3 e to the 9t. And then let's let negative 6 times c sub 1 be c, so we can just write plus c. Remember, our goal here is to solve for u, so because we have base e here, we'll now take the natural log of both sides of the equation. Here, when we apply the power property of logarithms, we can move the exponent of negative 6u, so we have a product of negative 6u and natural log e. So negative 6u times natural log e equals natural log negative 2/3 e to the 9t plus c. And since natural log e is equal to 1, we can solve this for u by dividing both sides of the equation by negative 6, or multiplying both sides by negative 1/6. So this simplifies to 1. So now we have u, which is a function of t. So let's write this as u of t equals negative 1/6 times natural log of negative 2/3 e to the 9t plus c. So this would be our general solution. And now we'll use the initial condition that u of 0 equals 3 to find c, which will give us our particular solution. Notice if u of 0 equals 3, when the input t is 0, the output or function value would be 3. So this would give us the equation 3 equals, we'd have negative 1/6 times natural log of negative 2/3. This would be e to the 0 since t is 0 plus c. Since e to the 0 is just 1, this would just be negative 2/3. Let's finish solving this for c on the next slide. Let's clear this fraction by multiplying both sides of the equation by negative 6. So that would give us negative 18 equals natural log of negative 2/3 plus c. Now here we can write the log equation as an exponential equation. Since we have base e, we would have e raised to the power of negative 18 equals negative 2/3 plus c, or we can exponentiate both sides of the equation, meaning e raised to the power of negative 18 must equal e raised to the power of natural log negative 2/3 plus c. Looking at the right side here, because we have base e here and natural log is base e, the right side simplifies nicely to negative 2/3 plus c. On the left we have e raised to the power of negative 18. So to solve for c, we would add 2/3 to both sides. So we have c equals e to the negative 18 plus 2/3. So now that we know that c equals e to the negative 18th plus 2/3, and we know the general solution was u of t equals, going back to the first slide, negative 1/6 times natural log negative 2/3 e to the 9t plus c. We'll now perform this substitution for c, giving us our particular solution. So we'd have u of t equals negative 1/6 natural log of negative 2/3 e to the 9t plus c, where c is e to the negative 18th power plus 2/3. Before we go, let's take a look at this graph over the slope field that corresponds to the given differential equation. We have our slope field graphed here in red. U of 0 equals 3 would correspond to the point 0, 3, graphed here in green. And the graph of our solution u of t is graphed here in blue. It's hard to see, but our function does continue upward along the y-axis here, passing through the point 0, 3. So notice how our function does pass through the point 0, 3, and it fits nicely in the direction field, meaning the slope of the segments along our function do give us the slopes of the tangent lines to our function. I hope you found this helpful.